actual quantum numbers, because things can start looking very familiar. And the question they typically ask you is something like, is this a viable quantum number for an electron in this shell? So you kind of have to make sure you cross out everything it can't be. So with that being said, question number 3 is how to calculate pH of acetic acid. Okay, so with that being said, there's actually a lot of steps we need to take to calculate the pH of acetic acid. First step, honestly, I think is the most important, is to verify / find Ka of acetic acid. Okay, and you're probably asking why? Because we want to know if it's a strong or a weak acid. If strong or weak acid. Why do we need to know that? Because based on knowing whether it's a strong or weak acid could save you a lot of work. Strong acids and weak acids dissociate differently. The key separator is that if K is greater than 1, strong acid. If K is less than 1, oh, I have my signs wrong. Almost did it again. K is greater than 1, less than 1, weak acid. Okay? So, they don't say it, so this is more of a theoretical question, but that would be honestly the first step. So let's refer back to our acids and bases sheet. So, we have for acetic acid, where is it here? I think I passed it already. There we go, acetic acid. Okay, it has a value of 1.76 times 10 to the negative 5. So acetic acid is a weak acid. Now that we know that, we need to now use the corresponding equation then for dissociation constant. So we have Ka is equal to the products, okay, which is going to be for acetic acid is conjugate base and H3O plus over its reactants, which is just going to be the conjugate acid. Okay, so to put actual values to it, if we have acetic acid, the formula is CH3COOH plus H2O. It doesn't count as a product because it is just part of the solution. It's an aqueous solution. It's in water, and it forms CH3COO minus. That's the conjugate base. Okay, plus H3O plus. Okay, so typically, actually, what you would see is that instead of CB and CA here, you would actually see A minus, because what's happened is that it just lost a hydrogen and HA there. So this is your HA and this is your A minus. So this right here is the formula for Ka. So if we're to bring it down to now for this specific acetic acid, it would be CH3COO minus H3O plus over CH3COOH. That right there would be your Ka. Now, with that being said though, okay, our work is definitely not done. The goal we're trying to do here is find specifically this, because this tells us, because remember that formula to find acids, the formula to find acids, right? I mean, to find pH, it's just pH is equal to negative log H3O, concentration of hydronium plus. That's really it. But the reason why is because it's a weak acid, we kind of have to go through a process to even get to this equation. Okay, so with that being said though, we kind of have the equation set up and we want to solve for the H3O plus. But I wouldn't go and try to isolate it from this equation here. I would actually use what we call an ICE table, okay? Which stands for initial change and equilibrium. Okay, the reason why we do this is because whenever they're asking you to find the pH of, I guess, weak acids in general, they usually give you or any acid really, they kind of have to give you the concentration of the acid. Like if I want to find the acidity of hydrochloric acid, I need to know the molarity of it, the concentration, moles per liter. So that's the initial amount we start with of the acid. So here's CH3COOH. And then we also need to list down the products. And H3O. Okay, so now, as I said, we're given the initial concentration of CH3COOH. So let's just make it a value. Let's say it's let's use X, like big X. I guess that's the easiest way to put it. Okay, and these are gonna start at 0, because usually when you solve these questions, they just said like that's the concentration of the acid and there's nothing else added to it. You have yet to form any of the products yet. Okay, that's why we start at 0 for these ones. And then we are now to factor the change. If we're going based on this equation here, we're going to have one of these. It's a 1-to-1 ratio. For every CH3COOH lost, which is the only way to go because you need to form your products. For every CH3COOH lost, an amount of CH3COO and H3O of that same proportion are made. So it's like this: plus X minus little x. So that's why they want to use X. I'm going to use Z. That's something that I don't think I'm going to use in this one. Or quantity. That's a better one. Q. Initial amount. Yes. So our total equation now for this ICE table is Q minus X, X, and X. And we're in a sense trying to solve for X, which is why I did want you to rearrange this equation here, because honestly just make things harder for you. You want to solve for X because you know that whatever value you have of CH3COO minus is the same as that H3O plus, as long as you didn't start with any of those products in the beginning before you even did your work. Sometimes they may say like, oh, a weak acid was added into the into a solution that already contained a strong acid, so there's complete dissociation. So you'd actually already start with a certain amount of H3O already, and that would definitely affect your change in pH. But before we even get over there, point being is this is how you set up this equation. Now, this is the part we have to stress because there's a breakdown in terms of two methods to solve this, okay? And the methods depend solely on this right here, the Q minus X, okay? It will change this part, that's what I meant. If your concentration, okay, is 1,000 times greater, so it's still bigger than 1,000 times the Ka value, then effectively, so this is if this, then Q minus X can be rounded to just Q. If not, you have to keep Q minus X is equal to Q minus X. You're probably wondering, how does that play into this? When you're actually filling your values for the Ka, you actually see, so we're using acetic acid, right? We have 1.76, right, times 10 to the negative 5, yep, is equal to, okay, because we have two x's now, CH3COO minus and H3O, so that's x squared over either Q minus X or just Q. So let's say exactly we had a concentration of, let's see, 1.76 times 1000. So if we had a concentration of 0.01 of the acid we're starting with, we have to use this one here, okay? And this actually simplifies into a quadratic formula. So you'd have to use a quadratic formula here when you actually reorganize everything. If it was greater than 0.01, so let's say we had like 0.02, like I would say minimum, that's a pretty good amount. You can kind of just round it off, okay, where you just have x squared over q, which means all you'd have to do there is multiply the concentration times the K value, the Ka, and then just do the square root of it. So that's why there's two ways to do it. Okay, let me actually switch sides because that way it's a little bit more coherent. Okay, so, oops. So overall, the point being is that, let's see, where am I? This is the one I want. Okay. So let me just not mess that up again. So we have this. Alright, so one requires quadratic and one requires that. The quadratic equation, okay, would kind of end up looking like this. So you multiply both q 1.76 times to the 5 minus x of that amount. So it would be x squared plus 1.76 times 10 to the negative 5x minus q times 1.76 times 10 to the negative 5, okay? So equals 0. So exactly, this right here is the b value you'd use in your quadratic equation. This 1 is your a value, and this right here is your c value. So you would have exactly the minus b plus or minus the square root of b squared minus 4ac and over 2a. That's what you use to solve this. You'll get two values, one of them being negative. That negative value you can just ignore because you cannot produce a negative amount of a product, okay? So exactly, that all that work, whether you use this way or the quadratic equation, will give you an x value. That x value you get, okay, is going to be your concentration of H3O plus and also the concentration of your conjugate base, as long as both of them started at 0 initially. But you really just want the H3O plus. And now that we've gone the concentration of H3O plus, we can finally go all the way back and plug it into here to find out the pH of acetic acid. So, as a quick summary, if it's a weak acid, you have to go through these steps because that's what they said, acetic acid. The good news is that every weak acid follows this kind of breakdown where you need the Ka value and everything else. And exactly, you end up finding the concentration of hydronium, which you then finally plug in to find the pH. So, with that being said, fun fact, if it was a strong acid, it simply dissociates completely. So however much the concentration of the original acid, you'll have a proportional equal to that. So let's say you start with HCl, because there's only one hydrogen there when it dissociates. In fact, actually, because most acids actually just dissociate one by one, it would just be that it's a 1-to-1 ratio the hydrochloric acids put in. So then, with that being said, it's going to be whatever moles you have of HCl, moles per liter, molarity, with the same amount of hydronium. Hence why it's a 1-to-1 ratio there. Okay, so with that being said, we have, yep, pH equals negative log H. It's also H3O, that one works too. And then CH3COOH. I like to always include the water part because this is actually what's happening in the reaction. It's not really dissociating per se. It's more so that this water takes away the hydrogen from CH3COOH. Okay, so that's why we have the hydronium. And then we have the Ka value. Yep, 1.8 times 10 to the negative 5. Yes, that is actually what we have here. Okay. And then x squared, which is a CH3COO minus plus H, times H plus, over the Q minus X, okay? Oh, they use Z instead. Oh, close to using that. But exactly, see the Z minus X, and then you solve for X. And then the value of X substitution into equation 1, which is the negative log H. And then you got the pH. So exactly. Depending on the concentration, is like you can either save yourself some work in just using that or the quadratic equation. If you're not sure, okay, which one you should use, default to the quadratic equation because that will always give you the most accurate answer. This equation here is kind of just a rounding system you can use to save yourself some time if the concentration is so big compared to the Ka. So let's go on to question 4.